Hi everyone. Today in this lecture, I would like to solve a couple of examples for different type of filters and see how the load can affect the filter parameter. Let's start with the first example. Let's assume that we have this circuit, and in this circuit, we are looking at the voltage of resistor. So here is our output voltage, and we're applying the input voltage of VI. The question is that what type of filter we have here. Obviously, we have a high-pass filter because in previous lecture we saw that if we have an RC circuit and we focus on the voltage of resistor, that's going to be a high-pass filter. But the main question is that what will happen to this circuit and its parameter if we add a load to the circuit. So let's assume that we connect a load equal to RL to this circuit. We want to know what happens to this filter, what will change, and which parameter will be different in no load and full load situation. Let's start with no load. For no load, we know that this circuit, which is an RC circuit, has a transfer function which can be described by a voltage divider, so it's easy to write the voltage divider. R over 1 over CS plus R multiplied by VI is going to be our output voltage. So if you rearrange everything and simplify everything, you're going to have H of S, which is VO over VI, as S over S plus 1 over RC. And that's going to be our transfer function, which is clearly, this is a high pass filter transfer function. Why? Because we're looking at first order polynomial in denominator, and our numerator is a coefficient of S. So it means that this is a high pass filter. If instead of S, we are looking at a constant number, then that's going to be a low pass filter. So we have a high pass filter here, and we know that the cutoff frequency of this high pass filter is equal to 1 over RC. So a high pass filter which has omega C equal to 1 over RC. So this is our filter situation condition in no load scenario. Now the next scenario that we would like to look at is full load or loaded. Let's call it as loaded filter. We want to see what will happen. So what I'm going to do is that if I have R and RL in parallel, then I can redraw my circuit in this form. This is my VI, which is connected to the capacitor, and then a resistor, which is equal to RL in parallel with R, and I have VI here, and this is my VO. Because the elements are in parallel, the voltage across the equivalent parallel resistance is equal to the voltage of each single one of them. So I still have VO here across this equivalent resistance. Let's call this RL in parallel with R as RX. So this is basically the same circuit as no load circuit, with the change that instead of R, I'm looking at RX. So I can get the same conclusion here, and I can say that the transfer function S over S plus 1 over, instead of RC, I have to use Rx multiplied by C. So what will happen is that still I'm looking at a high pass filter, but the cutoff frequency is equal to 1 over Rx multiplied by C instead of R multiplied by C, in which Rx is the equivalent of R and RL in parallel. Okay, now let's look at the frequency response and see how the magnitude of H at j omega will change for different frequencies. So what I can get from both of these two transfer functions is that both of them will approach, if S approaches to infinity or at high frequency, then the coefficient is equal to 1. So my magnitude will approach to 1. So no matter which one I'm looking at, for both of them at infinity, the magnitude is equal to 1. So the first conclusion is that the gain is fixed and equal to 1 for both loaded and no load situation. So for both scenarios, the gain is equal to 1. The difference is cutoff frequency. Let's assume that here I have omega C for no load filter, which means if the maximum magnitude of H at j omega is equal to 1, then the magnitude at cutoff frequency is equal to 1 over radical 2. Now, I know that, let's assume that this is the cutoff frequency of no load situation. So then this is going to be my filter. And then if I want to draw the loaded one, what will happen is that instead of 1 over RC, I'm looking at 1 over Rxc, in which Rx, which is the equivalent of R and RL in parallel, is smaller than R itself. So because Rx is smaller than Rc, then 1 over Rxc is going to be a bigger number. So the cutoff frequency of loaded scenario is going to be more than the cutoff frequency of the no load situation. So I'm going to have a cutoff frequency, for example, somewhere here, which means at this frequency, I'm going to have a magnitude equal to 1 over radical 2. So this time, what I'm going to have for my filter is something like this. So at the end, the gain for high frequencies is equal to 1, but the cutoff frequency of loaded and not loaded situation are going to be different. So the cutoff frequency of no load is going to be smaller than the cutoff frequency of loaded scenario. Okay, now let's look at another example and see what happens if we add a load to a particular filter. In this example, we are looking at the voltage of an inductor in an RL circuit. So we know that if we focus on the voltage of inductor in an RL circuit, then what will happen is that we're going to get a high-pass filter, but let's show that using its transfer function as well. So we know that the transfer function here is going to be VO over VI, and that's we can easily find this transfer function by doing a voltage divider. So by dividing LS over R plus LS, and then by dividing everything by L to bring it in the form of a standard transfer function. So what we have here right now is obviously a high-pass filter with a cutoff frequency equal to R over L. So this is basically our no load scenario. Now I want to see what happens if I attach a load equal to RL to the output of this circuit. This time, the loaded scenario is not going to be as easy as the previous example because it's going to be more difficult to merge the resistor and inductor. So what I have to do is that I'm going to figure out what is my transfer function in the situation that I have a load attached to my output with this circuit, which is this circuit. Okay, so in order to find the transfer function, this time I'm going to use another voltage divider to describe VO over VI, but the difference is that this time I have to focus on both of these two as my component that I have the output voltage across them. So I need to write my voltage divider in this form: RL in parallel with LS divided by RL in parallel with LS plus R. So now I want to simplify what I have here. So the parallel is going to be RL multiplied by LS divided by RL plus LS, and then I have RL multiplied by LS divided by RL plus LS plus R. Now what I'm going to do is that I'm going to multiply everything by this term. So what I'm going to have here is going to be RL multiplied by LS divided by, multiplying the denominator by this term will cancel out what I have here, so I ended up having RL multiplied by LS plus R multiplied by this term. So I'm going to have R multiplied by RL and R multiplied by LS. Okay, so now what I'm going to do is that these two, I can rearrange everything. So I'm going to have RL multiplied by LS divided by the coefficient of L and S here is RL plus R multiplied by L multiplied by S, and then the constant is R multiplied by RL. So now I'm going to divide everything by the coefficient of my S to make it looks like a standard form for a high-pass filter. Obviously this is a high-pass filter because I have S in numerator. So I'm going to divide everything by this term. I'm going to write it at the top here. So if I divide everything by what I'm showing you here, in numerator I'm going to have RL divided by R plus RL multiplied by S. The L here cancel out the L that I have here. And then in denominator, I'm going to have S plus R multiplied by RL divided by R plus RL multiplied by L. So let's see what I have here. What you can see here is basically the definition of R in parallel with RL. So let me rewrite everything in another page. So this is going to be my transfer function in loaded scenario. So obviously, again, I'm looking at a high pass filter. So it's anyway, with or without load, it's going to be a high pass filter. The only difference is going to be in omega C or cutoff frequency and gain. So the gain is not same as before anymore. So let's look at these values in no load and loaded scenario. So let's go back to the no load. In no load scenario, we had R over L for cutoff frequency, and our gain was equal to 1. So our gain was 1, and our cutoff frequency was R over L. Now this time, instead of R over L, I have R in parallel with RL divided by L. So R will be replaced by R in parallel with RL divided by L. And my gain has changed obviously, and the new gain is equal to RL divided by RL plus R. And you can see that this gain is smaller than 1. So what will happen in this case is that if you attach a load to a circuit like this, which is a high-pass filter with a gain of 1, not only you are changing your cutoff frequency, but you are also changing your gain. So this is a little bit different with the previous example. So here, if I want to show you what happens to the frequency response plot, this is what I'm looking at. So in the original scenario, my gain is equal to 1. So let's assume that this is the frequency response, and at 1 over radical 2 happens sometimes here. So this is basically at some frequency, which is equal to omega c for the no load condition. And for the loaded, this time, instead of reaching to 1 at higher frequencies, this time my maximum gain would be something equal to let's assume that what I have here is RL over R plus RL. So this would be the maximum gain. So finally my frequency response plot will reach to this maximum gain at omega approaching to infinity. And when I'm looking at the cutoff frequency, then I have to look at 1 over radical 2 multiplied by the maximum, which is RL over R plus RL. So this is going to be the gain at cutoff frequency, which is going to be something here. So what I have 1 over radical 2 multiplied by RL over R plus RL. So this would be my cutoff frequency for loaded scenario.